Imagine a computer chip fails in your 1977 vehicle. Now imagine it's in interstellar space, 15 billion miles away.
Saturday morning, we watched as Voyager 1, computer memory no longer working, something had failed.
Voyager 1 probe is sending usable information to Earth again.
3, 2, 1.
Voyager 1 has made a shocking discovery in deep space, causing a big stir. In the vast space between stars, where the sun's power fades, lies the Heliosphere, the edge of our solar system. At the heliopause, where solar winds meet interstellar space, Voyager 1, moving at 37,000 miles per hour, has unexpectedly found remains of ancient stars. What has Voyager 1 found that's so alarming? Let's find out more about the looming danger speeding towards Earth, the hidden challenges of space exploration. Voyager 1 carries a tool called the Plasma Wave Science Instrument, which helps study space properties. This device has noticed that the tiny particles in the space between stars are packed more tightly than those near our solar system's outer edge. This information is crucial as it changes what we thought we knew about where our solar system ends and the rest of space begins. This discovery is fascinating, yet also brings a reality check to our dreams of exploring space. The idea of traveling beyond our solar system has always been exciting. However, the actual conditions out there might be more complex and not as ideal as we once thought. When Voyager 2 ventured through this boundary 6 years after Voyager 1, it also noticed the same thing. This confirmation suggests that the boundary separating our neighborhood in space from the rest of the universe isn't as distinct as we once believed. These findings make us rethink our space exploration strategies and what it means to venture into the unknown. What does the future hold for space exploration? As scientists and engineers closely monitor the data from Voyager 1, they do so with a blend of curiosity and caution. Space, as we've always known, is full of surprises, some thrilling, others less so. As Voyager 1 and its fellow spacecraft venture further into the unknown, a pressing question lingers. Are we truly prepared for what space might disclose? In our desire to explore and decipher the mysteries of the universe, we must brace ourselves for discoveries that could fundamentally alter our current understanding. The cosmos, vast and unpredictable, may throw at us scenarios that challenge our preconceived notions and test our readiness for the unexpected. Whether these surprises are technological anomalies, unforeseen environmental conditions, or astonishing cosmic phenomena, we must remain vigilant and adaptable. The exploration of Voyager 1, a path of solitude and exploration, symbolizes humanity's relentless pursuit of knowledge. However, this quest is not without its risks. The further Voyager 1 travels, the more we realize how much we do not know and how much is left to discover. This reinforces the importance of preparedness and humility in our cosmic endeavors. When the scientists overseeing Voyager 1 analyzed the magnetic field data the spacecraft sent back, they expected to see some clear interactions between the sun's magnetic field and that of outer space. Surprisingly, nothing changed in the data, which left the scientists confused as they had not anticipated this outcome. It was a stark moment of realization that even with all their expertise, the universe still had surprises in store. Voyager 1 was experiencing what seemed to be a memory issue. For most people on Earth, forgetting minor details is usually harmless. But for a spacecraft billions of miles away, this can be a critical problem. NASA found itself in a tricky situation, as the spacecraft began to send back unintelligible data, disrupting months of scientific work. The situation demanded immediate attention because the consequences could mean losing communication with Voyager 1 forever. Efforts to fix the problem led NASA engineers to inspect the spacecraft's internal systems, specifically the flight subsystem, which manages data transmission back to Earth. They identified a potential fault in a single chip within the flight data subsystem. Correcting this issue was not straightforward, as each command to the spacecraft took nearly a day to reach and another day to receive a response. they discovered that about 3% of the FDS memory was corrupted, which significantly hampered the spacecraft's operations. The challenges were compounded by the fact that the technologies used in Voyager 1 were designed more than half a century ago. Most modern devices are not built to last so long, especially not under the extreme conditions of space. Moreover, many of the engineers who had originally designed and built Voyager 1 were no longer available. Some had retired, and others had passed away. This generational gap added a layer of difficulty in diagnosing and fixing the spacecraft's issues. The communication delay of 22.5 hours each way, due to the vast distance of over 15 billion miles, further complicated the diagnostic process. This delay made the troubleshooting process excruciatingly slow, akin to a painstakingly slow conversation stretched over days. Engineers were essentially making educated guesses about the spacecraft's problems, and each guess took days to confirm. To tackle Voyager's issues, NASA called back a retired expert, hoping his experience could save the mission. A forgotten engineer's last stand. A somewhat desperate measure, NASA even brought an engineer out of retirement to help resolve the issue. Bob Rasmussen, who had worked on the Voyager project shortly after finishing school and had retired years later, was called back. His deep familiarity with the spacecraft was invaluable, as many of his contemporaries were no longer active in the field. Rasmussen and his colleagues embarked on a meticulous review of old designs and documents, some of which had yellowed with age, to understand the underlying problems better. Each week, the team sent commands to Voyager 1 and awaited responses that would hopefully shed light on the issue. Progress was slow, and each new piece of data was critical to piecing together the solution. The situation was frustrating for everyone involved, but the team was determined not to give up. This ongoing effort by NASA highlights not only the challenges of space exploration, but also the relentless human spirit to overcome obstacles, regardless of the odds. As the team continues to work on restoring Voyager 1's functions, they are reminded of the sheer audacity and ambition of sending a spacecraft so far from home, and the reality that even our most advanced creations are not immune to the ravages of time and space. The problem the Voyager 1 team faced was serious. Should they just accept the new, flawed way Voyager 1 was communicating, or could they possibly repair the issue and get Voyager 1 back to working as it should? It's surprising this isn't discussed more, considering how well-known Voyager 1 and its counterpart Voyager 2 are in the space exploration community. Launched nearly 50 years ago, these spacecraft are more than just tools. They are symbols of human curiosity thrown into the vastness of space. The main goal for these space siblings was to visit the biggest planets at the edge of our solar system and go as far as the sun's power can be felt. Interestingly, despite being older and technologically less advanced compared to newer devices, these Voyagers have ventured further and taught us more about distant spaces than anyone had originally thought possible. Fast forward to today, and we're still grappling with the repercussions of decisions made decades ago, when there was immense pressure to excel in the space race. Take, for example, the confusing choice to launch Voyager 2 before Voyager 1. This odd decision caused confusion among many, including reporters who couldn't make sense of the naming strategy. The path of Voyager 2 began on August 20th, 1977, taking off from Cape Canaveral, Florida, on a Titan Centaur rocket. Following this, Voyager 1 launched on September 5th, 1977, on a trajectory that would allow it to reach its targets quicker than its twin. At the time, these spacecraft represented the pinnacle of technological achievement, equipped with advanced systems capable of analyzing planetary atmospheres, magnetic fields, and more. They could even take detailed photographs of distant planets and send these images back to Earth. However, the inclusion of golden records on both spacecraft might raise some eyebrows. These records, filled with Earth's sounds and images, were meant to communicate the essence of humanity to any extraterrestrial beings that might encounter them. While this was a hopeful and well-intentioned gesture, one has to wonder about the practicality of such an action. What are the chances that these interstellar messages will ever be received by other intelligent life forms? As Voyager 1 and Voyager 2 continue their path into the unknown, they remind us of the vastness of space and our small place within it. They transmit less and less data back to Earth, but they stand as a testament to human ingenuity and the longing to explore beyond our limits. These questions are not just about fixing a technical problem, but reflect deeper inquiries into the nature of our explorations into space. Are these missions a true reflection of human accomplishment, or merely attempts to reach into the darkness of space, hoping to find something more? These spacecraft, though aging and increasingly irrelevant in the fast-paced universe, challenge us to think about our place in the cosmos and the legacy we hope to create through our ventures into space. The plan to launch Voyager 1 and Voyager 2 was quite bold for the 1970s, a decade not known for cutting-edge technology. These spacecraft were set to capitalize on a planetary alignment that occurs just once every 75 years. This alignment would help by pulling the spacecraft along faster, using the planet's gravity, like a slingshot speeding them through space. Although this method was clever and new at the time, it seemed like the scientists were aiming for something extremely challenging. As Voyager 1's team struggled, Voyager 2's mission brought new discoveries about our solar system's distant planets. The ambitious mission that defied 1970s technology. Voyager 2's path was plotted to pass close to Jupiter and Saturn, then make its way toward Uranus and Neptune. Meanwhile, Voyager 1 had a slightly different route, planned to head sharply away from the plane most planets orbit in after swinging close to Saturn, specifically to pass near Saturn's largest moon, Titan. Titan was of particular interest because of its thick atmosphere filled with nitrogen, a rarity that intrigued scientists. However, the big question loomed. Was this goal too high for the 1970s level of technology? How were the engineers planning to keep these distant travelers moving and operational for decades without any refueling stops? Unlike a car, Voyager 1 and its companion weren't equipped with engines designed for continuous power. Instead, they were built to make small, precise movements to adjust their paths and ensure they stayed on course. Voyager 1 was equipped with a propulsion module that included 16 hydrazine thrusters, divided into 2 sets of 8. One group controlled the spacecraft's orientation, and the other made small corrections to the path it traveled. This hydrazine fuel was stored in a tank and distributed through a system of pipes to the thrusters. Although well planned, this system relied heavily on the hope that all components would work perfectly in the extreme conditions of outer space, a long way from any help. The thought that these meticulous path adjustments could be managed with the technology available in the 1970s might seem overly confident. After all, conducting a space mission with such precision is an enormous challenge, even with modern technology. One could argue that the planners of the Voyager missions were perhaps overly ambitious, betting on the success of a highly complex operation dependent not just on their calculations and designs, but also on many things going just right in the unpredictable environment of space. This approach to space exploration could be seen as quite a daring move, heavily reliant on the accuracy of their scientific calculations and the reliability of their engineering. It reflects a time when the boundaries of space were pushed by sheer will and technological ingenuity, despite the limitations of the era. The ambition behind Voyager's missions underscores a significant leap in space exploration, driven by human curiosity and the desire to reach beyond known limits, all hinged on a delicate balance of precision and good fortune. The Voyager spacecraft uses a thruster system where a chemical, hydrazine, interacts with a catalyst to break down into hot gases, creating propulsion. Yet, the more intriguing part of this system is how it maintains power over many years. The spacecraft's durability is largely thanks to its power source, a radioisotope thermoelectric generator, or RTG. This device doesn't rely on solar energy, which wouldn't be effective far from the sun where Voyager travels. The RTG operates by taking the heat from the decay of a radioactive material, specifically plutonium-238 dioxide, and converting it into electricity. This is done using thermocouples, simple devices that transform thermal energy into electrical energy. The choice of plutonium-238 by NASA was strategic, given its half-life of 87.7 years, which allows it to provide a long-lasting heat source. Originally, this setup produced about 470 watts of electrical power. However, as the plutonium naturally decays, the power it produces also decreases. NASA anticipated this and planned accordingly. They have been progressively turning off instruments that are not essential to preserve the remaining power. The cameras were among the first to be deactivated because, in the deep darkness of outer space, they serve no practical purpose. This mission, therefore, isn't just about what the spacecraft achieves or discovers. It's also about the broader implications of sustaining technology in environments where traditional energy sources like solar power are ineffective. It underscores the importance of planning and adaptability in missions that go beyond the immediate reach and into the unknown expanses of space. It ensures that even as physical power wanes, the legacy of the mission continues to enlighten our understanding of the universe. Beyond just spotting rings, Voyager 1 dove deeper into the atmosphere of Jupiter, sending back data and images that uncovered the complexity of its weather systems. These included intricate cloud structures and intense storms that change rapidly. The data provided by Voyager 1 wasn't just visually captivating, it was scientifically revealing. It introduced us to the Great Red Spot, a massive, enduring storm so large it could easily engulf Earth. This colossal cyclone, spinning in the opposite direction to most storms on Earth, has been active for centuries, showing no signs of dissipating. Voyager 1's discoveries also included lightning in Jupiter's atmosphere, a phenomenon that hadn't been considered possible on other planets. The spacecraft showed that Jupiter experiences thunderstorms similar to those on Earth, complete with lightning strikes that rival the intensity of those we are familiar with. This discovery corrected our Earth-centered perspectives, illustrating the universal nature of weather phenomena. Voyager 1's finds at Jupiter challenged our knowledge and expanded our view of space. The volcanic wonders of Io, Jupiter's fiery moon. As Voyager 1 continues to send data from the vast expanse of space, each new piece of information is a lesson in humility for humanity. It challenges our assumptions and adds to our understanding of the universe. The spacecraft's findings, from planetary rings to atmospheric storms and lightning, encourage us to reconsider what we think we know about our solar system. Each discovery gradually erodes our self-assured views, highlighting the unexpected and widespread nature of cosmic events. These ongoing contributions from Voyager 1 not only enrich our scientific knowledge, but also continually surprise us, proving that space still has many lessons to teach us. The enduring legacy of this spacecraft is a testament to the enduring curiosity and pursuit of knowledge that defines humanity's exploration of space. Each report from Voyager 1 is a reminder of the vastness and wonder of the cosmos, urging us to keep exploring and learning. From Jupiter's core to its moon's astonishing realms, Voyager 1's discoveries unveiled a series of revelations far more extraordinary and chaotic than previously imagined. As the spacecraft traveled through the Jovian system, it confirmed long-held suspicions about Jupiter. This giant planet is a turbulent, unruly force with atmospheric behaviors that dwarf anything seen on Earth. Jupiter's lightning storms, for example, were not just slightly more intense. They were a spectacular cosmic display, far surpassing any storm on Earth in magnitude and intensity. Voyager 1's instruments showed that Jupiter's magnetic field was not just a bit stronger than Earth's, it was significantly more powerful. This revelation wasn't merely for academic interest. It provided a glimpse into the colossal interactions between Jupiter's vast magnetosphere and the solar wind and charged particles, revealing the dynamics of cosmic forces that had been concealed from our view until then. Understanding Jupiter's magnetic field wasn't just about collecting data. It was about unlocking the titanic forces that govern the largest planet in our solar system. The moons of Jupiter, too, presented a landscape so alien that their realities seemed drawn from science fiction. Consider Io, one of Jupiter's many moons, where Voyager 1 observed volcanic eruptions sending plumes up to 300 kilometers into space, something never witnessed on any other celestial body. The discovery of these volcanic activities was not a mere interesting fact. It marked a significant breakthrough, demonstrating active geological processes occurring on a moon other than Earth. These volcanic plumes were clearly visible against the emptiness of space, originating from a volcano fittingly named Loki Patera. Io's surface resembled an artist's canvas, painted with molten sulfur and sulfur dioxide, displaying a range of stunning colors from yellow to green, black, and red. This painted a vivid picture of a moon that was far from dormant. These findings did not just expand our knowledge of Jupiter and its moons, they fundamentally altered our understanding of the dynamics within our solar system. Each new piece of information from Voyager 1, while fascinating, reminded us of our limited understanding, showing that each discovery leads to more questions rather than definitive answers. This underscored the reality that despite our technological advances, we are constantly learning from the universe, which continues to surprise us with its vast complexity and unending hidden. These explorations remind us that we are still uncovering the basic principles of the cosmos, always several steps behind the universe's intricate and vast mechanisms. Io, one of Jupiter's moons, is incredibly hot inside, much hotter than the fiercest volcanoes on Earth. This intense heat powers constant volcanic activity on Io. The materials spewed out from these volcanoes are so significant that they have gone on to form the beautiful ring that surrounds Jupiter. This isn't just a minor detail. It's a crucial part of what makes Jupiter's ring system so unique and interesting. The material from Io interacts with Jupiter's strong magnetic field. This interaction creates massive radiation belts and stunning light displays, or auroras, which are far more impressive than any natural light show on Earth. These processes are not just visually spectacular, they also highlight the powerful and dynamic nature of Jupiter's environmental systems. Europa, another moon orbiting Jupiter, presents a stark contrast to Io. Beneath Europa's icy surface lies an ocean. When Voyager 1 passed by Europa, it sent back images showing the moon's surface crisscrossed with lines in various colors, with red being particularly noticeable. These images suggest that underneath the frozen surface, there might be interesting chemical activities happening. Despite being an old moon, Europa's surface is surprisingly smooth and youthful-looking, with very few craters. This is unusual because, given its age, one would expect it to be heavily cratered from constant meteorite impacts. The smooth surface suggests two possibilities. Either Europa is geologically very active, which would renew its surface, or something else, like shifting ice or volcanic activity, is smoothing over old craters. Voyager 1's path past Jupiter revealed surprising details about its moons, Io, and Europa. The volcanic heartbeat of Io and Europa's hidden ocean. These observations of Io and Europa are more than just interesting space trivia. They are crucial for understanding how moons can vary dramatically. Io is a volcanic powerhouse, constantly erupting and reshaping itself, while Europa might be hiding a watery world beneath its icy shell, possibly with conditions suitable for life. Such discoveries challenge our understanding of planetary bodies. They show us that moons are not just simple rocks orbiting planets, but are worlds with their own unique features and processes. Every new piece of information leads to more questions, pushing scientists to keep exploring and unraveling the complexities of our solar system. As the path of Voyager 1 and its partner, Voyager 2, continue, their future is wrapped in uncertainty. These spacecraft are close to using up all their energy, and NASA is already getting ready for the time when they won't be able to talk to us or keep working because they'll be out of power. Despite this coming silence, many believe that Voyager 1 will travel further into space than any other human-made object, standing as a quiet symbol of human creativity and curiosity. However, the truth is that these pioneering explorers will eventually stop working and drift aimlessly through the vastness of space, far beyond any place humans might reach. This less romantic view can take away some magic we often feel about space exploration by showing that our achievements have limits. The image of Voyager as a lonely messenger of humanity in the vast emptiness is touching. But it also makes us see how small we are in the universe, and how much of it we have not seen or understood yet. The vast, unknown areas that lie beyond what we can reach today remind us of this reality. This perspective doesn't just highlight the end of Voyager's power, it draws attention to the boundaries of our current technology and the immense scale of the cosmos that remains unexplored. While our steps into space have been bold, the paths yet to be explored are vast and filled with for future generations to maybe uncover and navigate them. Every silent mile that Voyager travels is a testament to our reach and our limits, a floating reminder that there's so much more out there that we have yet to learn. Throughout the history of space exploration, numerous probes have ventured far beyond Earth, each revealing unique secrets of our solar system and beyond, illustrating human ingenuity and curiosity. Starting with the earlier missions, Mariner 2 made history in 1962 as it flew by Venus, providing the first data about its thick atmosphere and hot surface. This success was followed by Mariner 4's pioneering flyby of Mars in 1965, which offered humanity its first close-up views of the Martian surface. These initial expeditions set the stage for the more ambitious voyages that would follow. In the mid-1970s, NASA launched the Viking missions to Mars. Viking 1 and Viking 2 not only orbited Mars, but also successfully landed on its surface, conducting experiments and sending back detailed photographs that provided profound insights into the planet's geography and atmosphere. These landers conducted the first experiments aimed at detecting life, marking a significant milestone in astrobiology. Parallel to the Viking missions, the Soviet Union was making remarkable strides with its Venera program, which focused on Venus. Between the 1960s and 1980s, this program successfully landed several probes on Venus, transmitting back the first images from the planet's surface. Images that revealed a world with extreme temperatures and pressures, covered in volcanic plains. The 1980s witnessed the European Space Agency making its mark with the Giotto mission, which closely encountered Halley's Comet in 1986. This mission provided vital data on the composition of the comet's nucleus, adding a significant chapter to our understanding of these celestial wanderers. The landscape of international space exploration expanded with the involvement of new spacefaring nations in the late 20th and early 21st centuries. Japan entered the arena with its missions like Hayabusa, which astoundingly returned samples from the asteroid Itokawa to Earth, opening a new era of sample return missions from celestial bodies other than the Moon. The momentum continued into the new millennium with countries like India and China advancing their space capabilities. India's Mars Orbiter mission, launched in 2013, achieved a milestone by becoming the first nation to reach Mars orbit on its first attempt. Meanwhile, China's Chang'e missions have not only orbited the Moon, but also landed on it, including a historic landing on the far side of the Moon. Moreover, NASA's Near Shoemaker mission in the early 2000s orbited and eventually landed on the asteroid Eros, providing extensive data about its composition and orbit. This mission underscored the increasing interest in asteroids for their scientific value and potential resources. Do these silent voyages mark the limits of human achievement, or can we surpass these boundaries? Comment your thoughts below, and don't forget to subscribe for more explorations.